semester ago when I actually finalized, there was a kid actually, they were all in the certain room process in the science building. And so we have both our class professors there, and you just take whichever one you want. You know, most kids, you take one day, and instead you take the next one the next day. There was one kid, we were all in there taking one of our tests, and he walks out, turns in the test he did, grabs the other one, goes and sits back down. The rest of us just lost our minds. It's insane. Some people are built like that.
I always like being on like Learning Suite, and it's the last day, and it says like only 46% of tests have been handed out, and today's the last day. You're like, yep.
Oh my god.
All right, welcome nerds to the final review for Econ 378. I bet you're all very excited. I had said originally that this will go from 3 to 5. It probably won't be 2 hours. It can be 2 hours if you guys are so desirous. But it won't necessarily be quite that long for anybody who's worried about getting out of here on time. So I'm going to start by just reviewing a couple things, and then we're going to do some practice problems. We're going to talk about the practice test a little bit, and just general questions from you guys. The point of this review is less to literally go over everything we talked about in the semester and practice all of them, and more to help direct you over this next 24 hours of your own study in knowing what is most important. So as we talk about things today, I want you to ponder to yourself, why is Dan, in his infinite wisdom, talking about this specific principle? Because it might serve you well later on. So, we're going to start with just a couple of kind of review things, a couple topics from earlier in the semester that we may not have touched on in a little bit, just so that you guys remember that it's a thing. We're not necessarily going to do many problems associated with these principles, but I'm just going to go over them real quick. So the first thing is the MN rule from back at the beginning of the term. Who remembers what the MN rule is? What does that mean?
It has to do with multiplication, right?
It does have to do with multiplication.
Don't they have to be independent?
Yes, they are. MN rule does apply to independent things. Yep.
Probability of two things happening, you just multiply the individual probabilities together.
Exactly. You can multiply their individual probabilities together. So if one thing has a 1/3 chance of happening and the other thing has a 1/3 chance of happening, they collectively have a 1/9% chance of happening. And what we're really doing here is we're taking the number of possible, what the MN rule does is you take the number of possible outcomes as your denominator, and then you take the number of successful combinations, if you will, as your numerator. So if we have a 1/3 chance of picking one piece of candy and a 1/3 chance of picking another piece of candy, there are 9 total ways that we could pick a piece of candy and 1 successful outcome of picking the 2, right? If that makes sense. So MN rule, for independent things, you multiply them across. It's the number of successful, quote unquote, successful polls over the total number of possible outcomes. Connected to the MN rule is combinatorics, generally, which is possibly my favorite word, combinatorics. So you may remember N choose K from previously in the term. N choose K is really just a souped up version of the MN rule. And it tells us how many ways we can choose. Well, the MN rule the N choose K by itself tells us how many possible, successful outcomes there are, and then we can use that with an MN rule type principle in order to find probabilities. So when we do N choose K, let's say we have 10 things and we want to select 3. We do 3 factorial over 3 factorial times 7 factorial. So the general form is K over k factorial, n minus k factorial. And this tells us the total number of ways we can choose 3 things out of a group of 10 things. So, let's just say for the sake of argument that we have 10 pieces of candy, 7 of them are chocolate, and 3 of them are some sort of gummy candy situation. Deliciousness, if you will. So if we've got 10 pieces of candy, 7 are chocolate, 3 are gummy, and I want to know how many ways can I pick 5 candies. This is 10 choose 5, right? So this would be 5 factorial over 5 factorial times 5 factorial. And this will give me the total number of ways that I can just pick 5 gummies out of the 10. If I were to ask you, okay, what's the probability of picking 2 chocolate and 3 gummies? This guy represents the total number of ways that I can choose 5, right? So this is our denominator. Our denominator would be 5 choose, or sorry, would be, hold on, did I goof this up? I goofed this up, I think. This should be 10. This should be n. Yeah, that's my bad. It should be the total number of things over this divided. So if I said 10 choose 5, our total number of outcomes would be this. And then I want to MN rule the probability of selecting 2 chocolate with the probability of selecting 3 gummies, right? That would be the idea. So there are a couple of ways that we could set this up, but the way I'm going to say it is I'm going to say we have 7 chocolate, choose 2, and 3 gummy, choose 3, right? So this simplifies to be 7 factorial over 2 factorial times 5 factorial times 3 factorial over 3 factorial times 0 factorial over 10 factorial over 5 factorial, 5 factorial. I haven't worked out these numbers at all. This will be 1. I don't know what these are.
21 top left.
This is 21.
Yeah, 21 divided by 252.
21 divided by 252.
Or 8%, 8.3. So 7.
More gummies.
Behold combinatorics. Any questions on what we did here? How this was connected to the MN rule? Anything like that? We feeling loose? Feeling warmed up?
Oh, yes.
Oh yeah. Okay, moving on from combinatorics. We're going to talk briefly about probability trees, very briefly. So a good strategy for finding probabilities of intersecting events is to draw a probability tree. So if I say that there is a 50% chance of, I don't know, let's say there's a 50% chance of somebody going to Walmart and a 50% chance of somebody going to Target. And then if you go to Walmart, there's an 80% chance that you buy a Snickers and a 20% chance that you don't. I'm gonna put Snickers, no Snickers, Walmart, Target. And if you go to Target, let's say there's only a 60% chance that you buy a Snickers. People who go to Target obviously buy fewer Snickers than people who go to Walmart. And there's a 40% chance that you don't buy a Snickers if you go to Target. Now I can ask you for individual probabilities from this tree. I can ask you, okay, what percentage of the total population buys a Snickers? And you could say, okay, that will be 0.5 times 0.8, representing the percentage of people who go to Walmart and buy a Snickers, plus 0.5 times 0.6, which is the percentage of the populace that goes to Target and buys a Snickers. and this will be the total number of people who purchase Snickers. I could also ask you what percentage of the populace goes to Walmart and doesn't buy Snickers, and that would just be 0.5 times 0.2, and that would get you the total percentage of the populace. So these trees can be a convenient way to visualize intersecting events, when there's kind of a lot going on. Another thing we talked about early on real quickly, I shouldn't have to review this. I pray at this point in the semester that this is locked into your brains, but an expected value, an expected value of something is simply the sum of all of the values of that thing multiplied by the probability of that thing occurring, right? So expected value is also known as an average, and so if there's not like an obvious probability associated with it, you just divide by the number of things that there are, right? And assume that they're equally weighted. A variance, the variance is the expected value of all the x values squared minus the expected value squared, mu squared. Recall that variance is not just squaring all the x values and multiplying them by their probabilities. You have to subtract this second bit, otherwise you don't have the variance. And standard deviation is, of course, just the square root of the variance. So, very, very basic review of that kind of stuff. Remember that before we unlocked non-discrete numbers, we were working with charts where I would give you, I would give you a couple x values, maybe 1, 2, 3, and 4, and I would give you probabilities associated with those things, and then you could calculate for me expected values and things and variances using those different x values and the probabilities that I gave you. Eventually, we leveled up and we learned how to do this with probability density functions, good old PDFs. The PDF is just a function that I can give you. It could be any function. And in order to find an expected value with a PDF, we have to integrate it along all of the x values. And it's going to be the integral of the probability density function. I'll just put PDF here. It's the integral of the PDF multiplied by x. The reason why we're multiplying by x is because the PDF represents all of the probabilities of the x values, and then x is all of the x values, right? And so if we take the integral of this thing, we're doing exactly what we were doing before with an expected value, where we were multiplying each x by its probability, by multiplying the PDF by each of the x values. And this would be, of course, with respect to x. We then leveled up again, and we learned how to do this with joint density functions, so when we have multiple variables going on. And it's pretty much the same thing. Once again, if we're trying to find an expected value, we need to integrate it and multiply by the variable that we're looking for. We can also, if we're dealing with joint distributions, we can break them down into marginal distributions by integrating along a specific bound. So let's say that the original joint density function was something like 2x plus 1/2 y, IDK, double integral dx dy. If I wanted to find the marginal distribution of x, I could simply integrate this with respect to y on y's bounds. Let's say those bound for 1 to 2. If I integrate with respect to y from 1 to 2, its bounds, then I'll be left with a function only of x, which is the marginal distribution of x, which I can then use to find the expected value of x. the variance of x, and the standard deviation of x. All right. Recall that the CDF, so a PDF is just straight up a function, right? It could be like x squared plus 3 could be a PDF, possible PDF. The CDF is the integral of whatever that function is, right? The indefinite integral of whatever that thing is. And the way we find probabilities with either of these is with a CDF, you just have a function. So if we were to take the indefinite integral of this guy, we would get x to the 4 on 4 plus 3x plus c, but we don't need to worry about that. If I wanted to find a probability of this, I can just plug in x values associated with what I want to look at, and it will spit me out a probability. If I want to find a probability using the PDF, I just integrate it along specific bounds, between two values that I'm interested in, and that will spit me out a probability. Okay, that does it for PDFs and CDFs. And I think that does it for our speedy quick review of the term. Are there any questions on any of that stuff or any of the other kind of older topics from beyond the last 2 weeks or so?
Are you gonna talk later about like estimators or anything?
Yes, we will. We're going to be looking at, I think we're going to take a look at the practice test question about estimators. Sweet. Let's move along then. So on the Learning Suite, I have been so kind as to post a paper with some questions on it. If you'll pull up the Learning Suite and go to the Content tab, it is under the Midterm Reviews section entitled Final Review. So I have on this paper three questions on current material, one on older material, and then we're gonna go look at some things on the practice test. But just like we've done in previous reviews, I'm gonna let you guys get started on the first one, and then I'm going to be writing up the process for how to solve it on the board. And then we'll talk about each one just a little bit. The fourth question is a question from a homework assignment at like the beginning of the term, so I did not put that on the sheet. I just put the reference question, and you guys are gonna have to pull that up. Hopefully you've got your homework documents. And then we'll switch over to the practice test. So go ahead and get started with question 1. Hold up. Skip question 1 for now, actually. Go on to question 2. That's my bad.
What?
We may come back to question 1.
Is it written wrong?
No, it is written correctly. We just may or may not have talked about one thing you need to know to solve it. Which I just realized just now.
Like, we wouldn't know how to solve that?
Yeah.
Maybe you don't know how to do
Tell me what answer you got, Jake.
it. Rejecting the null.
We're the other
50-50.
Yeah,
50-50 shot.
that's what I was gonna do as well.
Now, really what we should do is a hypothesis test to figure out if test questions where you reject the null is greater than 50%.
That's a good
And
point.
then
Yeah,
you
that's a
can,
good
like,
point.
Oh.
But then you can like just have to know which one you should.
Did we talk about doing differences in standard deviations in class?
I don't know.
Testing to see if standard deviations are different or not.
I think we did some on the homework. They do difference in 50
That's what part 2 is asking for, is for you to, / question 1 was also asking about testing to see if the standard deviations are different. And if that wasn't covered in class, then we don't need to worry about coming on the test.
Would it be on the test? Or is it on the
I-
test since you've seen the test?
I don't remember specifically if it's on the test or not. If it was not mentioned in class and not done in the homework, then it won't be on the test. I'll run through how to do part B, and if it's not looking familiar to any of you, then probably safe to assume that it's not on the test.
It's essentially the same problem as 1 that we skipped, right?
Yes, yeah, it's the same type of problem. Okay, have you guys finished up part A?
Yes.
All right. So part A, classic confidence interval. Am I right? So you're asked to calculate a 95% confidence interval. Buzz over to your Z table if you haven't already memorized what Z value is associated with a 95% confidence interval, and you'll find that the value you're looking for is positive and negative 1.96. You can plug those in to your values, and then you stick that between, well, you find the difference in our recognized means, which is 0.5, and put that over the square root of the sample variances over the sample sizes.
So it should be squared, correct?
Correct. You are correct.
No.
No, because they're already variance.
They're already
Oh.
variances.
Oh, they're already variance?
Yes.
They're already in variance.
Sample variance. Oh, every time.
Gotta watch out for that.
Me.
I was tricking you. Clearly. This bit right here, this 1.96 multiplied by that is your margin of error. So typically the way I'll write the stuff, this stuff out is I'll put the difference in the means plus or minus my z-score multiplied by the sample variances and their sample sizes. This bit is your margin of error. Once you apply your margin of error to your difference or to your mean, depending on what type of confidence interval you are looking for, that will yield your confidence interval. So the margin of error is simply the distance between the center of your interval to the edge of your interval. It's the radius, if you will. Did you have a question?
No.
Looked like you had. Okay, cool. We're live.
I was just fixing my mistakes.
As we all must. So, real quick note, confidence intervals and hypothesis tests are obviously related ideas. We're oftentimes using the same numbers and the same kind of processes, but they're two very different things. A hypothesis test is used for analysis and used to determine if our assumptions about the world are correct. A confidence interval doesn't test jack. Confidence interval is just us spitting out where we think a true mean or a true standard deviation or whatever it may be. It has nothing to do with the test, so if you ever see, if you're asked to test for something or if you're given a level of significance, you're doing a hypothesis test, always. You'll notice that with confidence intervals, we have no assumption or idea about what the true mean is, or what the true difference in means is, or what have you. That's why we're creating a confidence interval, is we're saying we're pretty sure it's in here, right? When we do a hypothesis test, we have an assumed value for this parameter, right? And then we plug that value in order to run our test. So confidence intervals, we're saying nothing about what this is previously. In a hypothesis test, we have some assumption about what that is, which represents our null hypothesis. Part B, does this look familiar at all? Dividing by standard deviations and such. So I don't think we talked about this in class this term, but essentially the process here, if you're running a hypothesis test and you're looking for a difference in standard deviations, the process that we do this by is via ratio. So our null hypothesis is that the first, that one standard deviation multiplied, or one variance divided by the other variance equals 1, and then our null hypothesis is that it does not equal 1. And then our test statistic is simply calculated by finding the ratios. I don't think we talked about this in class though, so I wouldn't worry about this if I were you. Do we have any questions on confidence intervals, hypothesis tests? I'm going to mention one thing right after this quickly about proportions, but anything on these things?
Maybe one on when we're doing a variance test, hypothesis test, can we go over real quick how you determine whether to use the left or right side of the chi-square distribution?
Yeah. Let's see. So chi-square gives us, when we look at our table, all the values for chi-squared, it gives us what lies above, right? Always. And so, so say the 0.995 chi-square value lies all the way down here, and then it gives us everything above. And when we're running a hypothesis test for this, we're always looking for extreme values, right? That's the idea of a hypothesis test, is we're looking for where the extreme values lie. And so if we say are looking for, nice to have an example to look at. I'm going to pull up the homework from just a bit ago and pull up an example.
For that first question, we would use chi-squared, right? About comparing the variance of wait times at the restaurants?
Yes. But that question then goes in to ask about, the first question asks, perform a hypothesis test to determine whether the variance of wait times at restaurant A is significantly smaller than the variance of wait time at restaurant B. So that leads into what, this whole side of things that we don't need to worry about. A question that would be more likely, that you'd be more likely to see, would be if you just had one restaurant and it asked you about whether or not, the sample variance was equal to some assumed, population variance. Let's see, let me pull this up real quick. Okay, so this guy from question 3 from the last homework gives us a null hypothesis that the population variance is 100, and then an alternative hypothesis that it is greater than 100. And then it asked us to test at the 1% confidence, right?
Okay.
And so we are looking for the point, for our critical value, we're looking for the point where 1% of values lie above
Right,
that line,
okay.
right? So we would just toss down this and go to the point 0.01, sorry.
Yeah, okay.
And that would give us that. And so, I mean, it's very similar to, you know, Z-table confidence testing.
Right.
If we're looking for greater than, we're going to be looking at the top of the distribution, less than bottom.
Okay, awesome.
Just the numbers, like the numbers here will be flipped because
That makes sense.
it shows just what's above.
Awesome.
With confidence intervals, real quickly in chi-squared, things can get a little zany because with a z-table, if you're looking for a confidence interval, say 95%, you're looking at positive and negative 1.95 as your value, right? With chi-squared though, it's not, you know, it's not symmetrical. And so you're gonna have two different values, two different chi-squared values. I'm gonna call it chi-squared 1 is less than our estimator, which is less than chi-squared 2. So originally when we look at this, right, chi-squared 1 is going to come from down there and chi-squared 2 is going to come from up there, right? But once we rearrange this to get sigma squared by itself, we're going to end up with, let's see, divide by that. So we get this situation. It's greater than sigma squared, which is greater than this situation. So it kind of flips around because we have to invert it. And somebody pull up their chi-square table.
Oh, got it.
Do the chi-squared values get bigger or smaller as you move up the distribution?
Moving right down.
Yeah, as you move right. As you move right on them.
Bigger.
Bigger.
They get bigger and bigger, right?
Mm-hmm.
So chi-square value 2 is bigger than chi-square value 1, right? That makes sense?
Correct.
So originally, we have small number is smaller than something which is smaller than big number, which makes sense, right? And then we invert it, and now we're dividing by a big number here, and we're dividing by a small number here, which means this ends up being big, and this ends up being smaller. So then we have small number is smaller than thing, which is smaller than bigger number, which makes sense, right? Even though we're kind of flipping things around and doing weird algebra in the middle of it, it still makes intuitive sense when we get to the end that you'll have small is smaller than thing that is big, right? Alrighty, let's do question 3 in the, oh wait, actually before I do that, let's talk really quickly about proportions. Dr. Price mentioned in class the other day the nuances with p hat versus p in our tests and things, which, not to plant my flag in the ground, but I did mention in my office hours prior to the correction. But I should have been more on top of things during class. But the idea is, if we're finding a confidence interval for proportions, we have our p hat plus or minus our test statistic or, you know, z-score or whatever, and then we have p 1 minus p over our sample size, right? So, like I said earlier, the difference between a hypothesis test and a confidence interval is that in a hypothesis test, we have an assumed value for the population parameter, right? Versus in a confidence interval, we have no such assumption. And so if we have no assumption about what p might be, then the only value we can substitute for it is p hat. That's our only thing that we can throw in there. So it makes sense that for confidence intervals, we're going to use p hat under this square root, because it's the only number that we can plug in there, right? When we move to confidence intervals, now we have an assumed value for P, right? We are assuming that P equals something from our null hypothesis. So it makes sense that we plug in that assumption everywhere where P is, right? So now we're going to use the null hypothesis P in this equation under the square root. I'm going to put a little null symbol to represent the null hypothesis. So I know that can be confusing. You know, sometimes we're using p hat for all these things. Sometimes we're using p. I hope that helps clarify why we're doing that and also helps cement some ideas about what makes a hypothesis test unique from a confidence interval. Yeah.
If we're doing like difference in proportions, we'll always use like each specific p and hat, right?
Yes, exactly. And we didn't talk about p pooled, right? Okay, we're not going to worry about that. All right, let's now move on to question 3 in the review, which is about regression. Very fun. Where are we at? Feeling good? Raise your hand if you've already finished up the question.
All
The
three
whole
parts?
question?
Yeah, all 3 parts. Oh, nothing? Okay, no, you're good, you're good. Vibe.
Are we is it asking for the proof, basically, of, like, to find the estimate for, like, beta 1 and beta?
No, it's just literally asking
Just
for it.
asking for it?
Yeah.
Okay.
just, yeah.
Maybe.
Thumbs up. Okay, we're going to talk about this briefly. I was very kind to you, exceedingly benevolent, because I offered you pretty much all the information you needed to solve all of these questions without actually having to calculate much. So beta 1 hat, our estimator for beta 1, is equal to the covariance of our variables over the variance of x, which very conveniently was given to you in the question. The covariance of x and y being negative 1.8 and the variance of x being 0.2. This can also be rewritten as rho, or the correlation of x and y, times by the standard deviation of y over the standard deviation of x. And this is some pretty simple algebra that you can solve for this. Rho is equal to the covariance of x and y over the standard deviation of x times the standard deviation of y. So we multiply that by standard deviation of y over standard deviation of x. These two cancel out. Standard deviation of x times standard deviation of x is standard deviation squared of x, which is variance, right? So this is covariance of x and y over the variance of x, right? How are ways we could have made this much less fun? Well, I could have given you a joint PDF for x and y, and I could have asked you to solve for this, which, like I said, I don't remember exactly what's on the test, but I'm pretty sure I had a question like that on my test, where I was given a joint PDF and asked to solve out for this. And the process, though, the process is just long. That process is long, but all you need to do is calculate the covariance and the variance, right? Do you know how to calculate a covariance with a joint PDF? Yeah, you just double integrate the joint PDF multiplied by x and y, right? And then subtract away mu x times mu y, right? That would find you your covariance, and then you can find the variance of x by integrating the marginal distribution of x times x squared minus mu of x squared. This would get you the variance of x. And now you can solve for B1. It's just a much longer and more annoying process. But as long as you know that, hey, B1 is covariance over variance, you can solve it out from any step of the process. I could give you these, I could give you the joint PDF. I could give you just values for x and y, right? Kind of like the tables we used to do before we started working with PDFs, which I think we've done some examples like that in the homework or in class. But it's the same process. Once you know covariance over variance, you can chug through from various parts, various points in the process. All right, B naught is always the easier of the two to solve, right? Because B naught is just finding the y-intercept. That's all we have to do, right? And so we can just plug in our newly found B1 value into our equation and we find B naught. Pretty simple to find most of the time. And then once we have the two of them, making predictions is also very easy because now we have our y-intercept, which we found in B naught, and we have our slope, which we found in B1. So now making predictions is just simply plugging in whatever x value it asks us to plug in, right? Yes, sir.
This is just maybe a throw out question. So just looking at the wording and stuff, and we're figuring out, because you gave us a covariance, variance of x, figuring out from this, like if it's the rate by professor wording or the number of openings, like determining which one's going to be x and which one's y.
That's a good question. Which one is the dependent variable and which one is independent? I would say for the most part, it will be reasonably clear. Like they might even tell you like this is dependent on this. For the most part, that would be the case. Intuitively, you can think about it in terms of, well, which one is more likely to be causal or more likely for me to use as causal? Am I going to say that somebody has a really high rate my professor score because nobody can ever get into their class? Probably not. It's probably that people have trouble getting into their class because they have a high score, right? And so that would indicate that that openings in the class would be y versus the score would be the independent variable. What's a good strategy? I would say no, for sure. Like sometimes it's definitely ambiguous, There was a homework question very recently about home construction or something, and it was it was like square footage of the house and then the amount of time that it would take to build, right? I would say like the questions that you'd be more likely to see on the test would be more like that, where there's a clearer connection between, what is the thing causing the other one, If it's bigger, it's gonna take longer, right? But any other questions on OLS regression?
What does OLS
What does it stand for? Do you know, Patrick?
Ordinary least.
Yes. Ordinary least squares.
Is that critical information for me to have?
It does contextualize the next bit of information, which is this didn't ask anything about errors.
Yeah.
But I would say there's a reasonably high likelihood of there being some question on the test saying, prove that the average of residuals is 0 or close to it, and or asking you to find the correlation between X and the errors. Yes,
We can
Bella?
go over the practice, like this question on the practice exam.
We can look at it if you want.
I have a question on it, but I don't wanna ask it, we're gonna get to it later.
I hadn't planned on talking about it previously, so if you've got a question, let's talk about it.
So there's one that says give an estimate for the standard error. What? And then it gave an equation that's SE.
Which number is this?
Question 4B.
4B.
Okay. Give an estimate of the standard error of the residual term. Let me contextualize this real quick, okay? So, all this is asking for, in terms of standard error is what is the average error size? Like on average, how far are the realized data points from the estimated data
Or
points?
should be 0, or
Well, so yes and no. When we look at, I should rephrase what I originally said. So the average of the residuals should be 0, but that does not mean that the absolute value of their distance from the line is 0. So what this is asking for is it's a
asking
measure of
looking
distance.
At the distance, not at
Because when we
necessarily
talk about
whether it's positive or negative.
Yeah. When we talk about the average of the residuals being 0, what we're trying to prove is that this is the best fit line, right? This is now asking for, okay, this is the best fit line, but on average, how far away are these points from the line? And once we are looking for distance, we no longer take negative values into effect, right? And so here we've got negative values that are canceling out positive values. And so if we take a simple average, it's going to end up being 0 or close to it. This question is asking for standard error. So think about standard deviation. So we're going to be squaring it at some point in this process. That's going to get rid of the negative signs. And then we're going to be left with some absolute measure of distance, right? And so in this question, they first calculated what all the error terms were, and then they squared each of them in order to get an idea of distance and took the average of those squared values, and then they took the square root of that.
Yeah,
Yeah.
I understand all of that, except on the keys, you did 1/4 minus 2. What on earth does that mean? Why is it 4? Shouldn't it just be 1/4?
Tis a good question. Tis a very good question.
It's just an average of 1/4
Somebody
times
call it
the
price.
squares. But I have no idea why he subtracts 2 from the denominator.
Let's see.
Or why is he multiplying by 1/2?
And the next question, you bet.
And then on the next question, part C, he uses that answer to do something else, so I don't know.
Let's see. Let's see if I can explain that.
Yeah.
Let's see.
I'm like, no.
So he's finding the variance, and so the 1/4 minus 2, I think the 2 might be a typo, it's probably supposed to be 1/4 minus 1.
1 minus 1 though.
Because it's the sample variance, and there's 4,
So it would be the
Samples
degrees of freedom.
But is it like
Yeah.
the party tricks? You do like V over V minus 2 and it's a T distribution? So that's why it's subtracting it by 2?
It's minus 2 times 1.
is it minus 2?
For a T distribution. Like, like variance of t equals variance over variance minus 2. But I don't know if this is
But
what we're
that's,
doing.
and that's not necessarily the variance, but it's like, it has to do with degree of freedom, I think. But,
That was my only reason why I thought it was supposed to. Because this is the only time I've seen it.
it's the same as.
Yeah. I totally forgot about that.
So
So maybe it's supposed to be.
Standard
4 minus
error.
2, but that does say V over V minus 2.
So I don't know if like
Two
V
over.
means variance and then the other V
I know,
is
why
degrees
is
of
it
freedom. Like they're, maybe it's two different
In-
V's?
That's possible.
In the T distribution I'm talking about, V is the degrees of freedom, so
Yeah.
it's V over V minus 2.
Yeah.
Oh, wait, but.
Like maybe the V's are different, like that V is variance,
And
the
then the
top
other
V,
V
and the
is
bottom V
degrees
is
of
degrees of
freedom.
freedom. Maybe, maybe not. Cause I think that's
No,
this problem.
because that's all
No, 'cause he's not
calculated variance.
Mhm.
So there's a capital V off to the side that's
Yeah.
equal to the V over V
That
minus
makes
2.
sense.
Plus, the other one, it wouldn't be, if it were V minus 2, it wouldn't be 4 minus 2, it would be 3 minus 2. Because there's 3 degrees of freedom with the 4 observations.
Oh,
Yeah.
that's right.
It just seems like it should be 1/4 times all of the squares of all the errors.
Or 1/3. There, I can,
Sample variance.
I can just plug all of this into the calculator and see what it comes out as.
The question is ChatGPT and see what happens.
It doesn't.
Is ChatGPT a girly
It's kind of says she.
because okay. So we're looking for the standard deviation of the errors, right? Which means this should be equal to the
Is that what we-
expected value of the errors squared.
Well, it says to give an estimate for the standard error. Is that what that is? Standard deviation of the error?
Yeah, if you see standard area sigma subscript e.
Oh, okay.
So standard deviation of the errors. So this formula should hold true, but since we're estimating it, I think that we put this whole thing over the square root of the sample size. Which in this case would be 2, because there's a sample size of 4.
But
I don't know why he's subtracting.
Minus.
He also isn't doing this part.
So
He's just squaring the values,
But
right?
sounds like you found
So
And
he
then
variance.
he's
takes
not
the
subtracting.
errors for each estimate and then squares them, but then multiplies that sum times 1/4 minus 2, which makes no sense.
And then takes the
And
square
the
root.
top of that
It's-
should be square
That's
root,
what I
right?
learned.
Yeah, the square root of all that.
Yeah.
So that's not what he's doing.
Well,
Because that's not at all what he wrote.
so
He's just not subtracting.
Does
Which,
it come-
when I look at his resulting number of 0.714, that is more than the square root of the average. So his value might be wrong in this key.
And then C, like the equation that he used, I don't really know what that is.
So in part C, he's using, wow, this is going deep.
Yeah,
This
we
is a
never
deep
talked
question.
about
We
this.
never talked about this at all.
Oh, that's just.
Does he make the practice exam, or does he take it?
Yes.
He does.
Yeah,
Oh, I'm
he
just
does
so
make
excited to
practice.
see. So far, we've talked about like 5 questions and like over half the stuff we never learned.
Kinda spooky.
So if the
Kinda
exam
spooky.
follows the same distribution that so far the review has, it's gonna be a
You're
bad.
50%.
Let's
It's
see.
easier than
Give me just 1 second.
Yeah.
That'll be.
So,
If it
Daniel,
isn't.
the way he calculated the variance is correct. Like, he didn't have to necessarily do it that way, because he, like, if you're working off a distribution table, that would be good, but because he has all the individual samples,
I
it's
literally,
easiest to just sum them all
like,
out.
cause I found,
So what he did there is valid.
it's question 4.
Because you were talking about, you were saying he didn't calculate this term and subtract
Yeah,
the mean square, right?
Yeah.
You wouldn't know.
That
He-
he's doing
Because what he did instead, he just actually did
Should I screenshot
Give
this
an
or just
estimate.
what is going
What's
on?
going
epsilon minus
I
epsilon
never
bar.
really showed you.
This is what he did, which is
You
valid.
probably would not.
Did he do that? I don't
Yeah.
believe he did that.
You probably would just.
Wrong thing. Where did it go?
I-
Because he. Oh, actually, maybe he did.
So,
do
because
that.
they're all mean, the mean is 0,
I
right?
had one of my professors that they had this.
Because we know that the error terms.
You're right.
Over
That is true.
50%.
That
So
is
it's the
true.
error term minus 0 squared. out
Yeah,
of
that's
all
that's a good
I
point.
was like-
Yeah, that is correct.
And so the only questionable thing is whether it's 1 over
And then that
2 or 1 over 3.
It's true, it
Is that
does,
only-
it would incentivize.
I think it should be 1
If we have
over
12 people in
n
class, we don't
squared.
have to convince that many people, and 2 of them are
I think
dumb.
that
If we just don't take
that
the exam.
that is.
Everybody
Well, let's see.
Hear me out, and then they curve it, then
That's
we'll all
big
just
bad.
keep
So
working
this-
towards it.
He's
Yeah.
like,
should
so the
be-
average time for the test was 3 seconds.
If we're doing sample variance, right, it should be
I would just don't
1
even none of
over
us,
I feel
none
like-
of us go.
n
I feel like
minus
We all would have
1.
to like
What would
pull
I think
all
we
night
have
here,
equals 1
so then
to
we keep each other
n,
accountable.
Right.
And then minus 0
Next 48 hours.
Yes,
squared.
And when
Right.
you guys have done anything for the class, goes takes it, and then we're all.
And then
We
you
have to
take
be
the square root of this, and that gives you the variance.
Well, I'll be the
And
same
then
thing. We're up
this
in
is
the mountains.
over n
Yeah.
squared root
Yeah.
n, which
Well,
is
no,
the
I'm
standard
saying,
error,
regardless
right?
of that, just
Anyway.
if we just, none of us take
So-
it,
Uh-huh.
then they curve us, then we'll
In
all of our grades
here,
will be
that
the
should be
same
1 over
amount.
4 minus
So
2,
you'll just have the same.
or
we have now.
4 minus
minus
1.
Which I'm fine with.
So it should be
I'm fine with
can live with
1/3.
So we just say, forget the exam, nobody take it, and they'll curve us back to where we go.
I'm
Yeah.
Don't let Dan hear.
I'm 99% sure that there isn't a question like this on the test. So I'm just checking.
Yeah.
Does that work? If nobody.
Uh,
If absolutely no one, like,
Cause then they would just curve it.
I looked at the election notes for like standard error, I committed F, and I couldn't find it.
Yeah, there's nothing there.
is there anything in the textbook that?
I'm sure there is.
So I think the
I
high
thought
level.
I
Not
expected-
use the textbook all
So
the
Dan,
time.
I think the high level question is, you saw the test, is this on?
That's what I'm looking at right now.
Fantastic.
Why don't I just pull up the test and we go through it? So that way we're done with it. That would be pretty awesome.
This gives me a little more confidence though.
Yeah, I felt
I
so
felt so
dumb doing
stupid
this. I was
doing
like, do I
this.
not know this?
So I looked at the-
Yeah, don't worry about that.
So the real question is on this test, how much stuff do we have to go, oh, do I not remember this, or is this not a real thing?
So focus, Jake, on everything that I've told you specifically to learn. Know how to find that the average of the residuals is 0. Know how to show that the covariance of x and epsilon is. Be able to find B1 and B0.
But is that whole adding up all the errors and dividing by the total, like averaging them, that's a thing?
But then the word.
What do you mean by
So I
that?
have all the errors, so I have like a, where it has like the error,
Do we have
the
to go
distance
step
between
by
the
step?
regression line, like the estimated value and the real value. And then, so each individual error term, so you average those, that's what what is that average called?
That's showing that the average of
It
residuals.
should be 0.
Yeah, that should be 0.
Yeah, because you technically.
Yeah.
did
And so you just have to
divide
show
in
that
order
that's-
of squared,
Right.
yeah.
Uh-huh.
But that makes sense, the thing.
Do we need
about-
understanding
yeah,
of the-
exactly.
Standard error.
But no.
Yeah, I think we just talked,
No.
Would it
nothing
be
about
this?
it. Fantastic.
And that, again, that wasn't talked about in class. So if something wasn't talked about in class, it's not going to show up on the exam because there's no expectation that you bought the textbook or that you read
I
the
just have
textbook.
like below.
Yeah.
So,
Can you
why
think
is it
of
at
practice exams?
Huh?
Why is it on the like example exam,
Covers all
like
of
the
them.
practice?
He like I must have forgotten that we didn't cover a specific thing, and so
I'm
put
just
it on.
wondering
Since
what
the
the
course
things
has
that I
changed,
didn't cover when you wrote
there are a couple things that we have not covered that I covered in my time in the class and that we covered last term, and so those are things that I had planned to talk about, but we don't have to know about them because they were never gone. So don't worry about those things.
So,
because
Yeah.
we found errors, well, actually,
Did we
It's like,
figure out,
maybe it's
like
not.
why
It's like,
what
it's
was the
4 minus 2?
We'll not worry about it. Let's just not worry about it.
Yeah, let's.
Let's talk about that after.
Well, if that's wrong though, do you think we can get extra credit for finding a mistake in part of the thing that we didn't even learn about?
I doubt
Probably not. He would probably appreciate it, but
Right there.
Including in the part C, it says
Yeah.
4 minus 2,
Right,
so
right.
I doubt he made the same mistake twice.
yeah, it likely is not an error. It's not something I've ever talked
But it's
about,
inconsistent.
and it's not something we talked about in class. So
I vote we don't talk
But
about
it found its way into the test.
Mine.
So there's a real
I
high
agree.
chance that it found its way into the test.
Oh, guys,
That's
this
what
is
I'm
our
saying.
statistics. What's the probability that it's in the test?
okay,
James said 100%.
let's.
Probability that we fail given it's in the test.
100%.
High. But if none of us take the test, then again.
We should have done this the entire.
Okay, let's go ahead and move on. While we're in the practice test, let's look at the estimator question real quick.
4 people, so.
What are we looking at?
The estimator question in the practice test.
Oh, yeah.
Which one is that?
6.
This one for,
Oh.
how cute.
This is a very benevolent estimator question, I think, actually, which should make you all happy because I would say that the practice test, as we've seen, is harder than or equal in difficulty to the exam. So, or potentially completely
We're
different.
salty.
Jake is very salty. Jake needs to humble himself. So, question 6 gives us it gives us what the expected value already is of this estimator. It tells you that the expected value of your estimator, theta hat 1, is equal to n theta minus 1 over n plus 1. It also very benevolently gives you the variance of that term.
Do you say this is hollow or equal to the test, you said?
Yeah. N plus 1 squared.
I still get it wrong. What are you ranking on it?
Question 1 asks you to find the bias of this. How do we find the bias of something?
The expected value of, I mean, you set the expected value of the parameter, and then you find that, and it should be equal to what you're measuring with the parameter.
Exactly. So bias of the thing is equal to the expected value of the thing minus the thing you're trying to estimate. And if it's unbiased, this will be equal to 0. If it's equal to anything else, then it is biased and it's hot garbage. Again, very benevolently, they've given you the expected value of this estimator. With that being said, I would say it's unlikely that on the exam you would see a question where it asks you to find the bias of the estimator. It's easier though than it seems to find the bias of an estimator. Well, not the bias, sorry, the expected value of an estimator. Because most of the things in an estimator are constant terms. The expected value of a constant term is the constant. So then the only thing you really need to find is the expected value of whatever variable is in your estimator, right? And in that case, it would give you some information to find that. It might give you some sort of PDF to find the expected value of that variable, or it would just tell you what it is. But it would give you a way to calculate that expected value, and then you just need to plug that into your equation. Not super crazy, but in this case, we've been given the expected value, so we plug this in, minus theta. You know, I don't want to spoil anything. I don't think this is going to be 0. But in order to combine these fractions, they need to have common denominators, right? So let's multiply this guy by n plus 1 over n plus 1 to get common denominators. So we get n theta minus 1 over n plus 1 minus theta, well, n times theta, we'll write it the same way it's written over there, plus theta over n plus 1. It's actually closer than I thought. These two terms are going to cancel out, and we get a theta minus 1 over n plus 1 is our bias. Right? Nope, that's a lie. Negative theta. Negative theta minus 1. Does this over or underestimate consistently? Under. Why is it under?
Because that's negative.
Because it's negative. It's a negative term. So this underestimates. Part B asks if it is consistent. What do we need to know for it to be consistent?
Variance. Oh, consistency.
As n approaches infinity, yeah, then the bias goes down and the variance goes down.
Yep, both of them go to 0 as n goes to infinity. So if we take the limit of the bias as n goes to infinity, our bias is this guy, right? If n goes to infinity, this becomes stuff over infinity. 0. And then we take the limit as n goes to infinity of our variance, which was also given to us. We get this. Again, we have stuff over infinity squared. Sounds to me like
Squared 0.
0 squared. So 0. So this is consistent. Even though it's biased, it is consistent because its bias and its variance go to 0 as n gets big.
And just to recap what that means from
Yeah.
our
Archery now.
all the arrows are close together, but not on the bullseye, like somewhere else.
So
Because it's biased, but consistent.
So you're talking about efficiency.
Oh, that's
Efficiency is a
efficient.
measure of how tight the arrows
Okay.
are.
Forget it then.
Can-
That's compared, right? Like, it has
Yes.
to be two values that we're comparing.
Yeah. Consistency is not like an absolute kind of term. We can only say if something's efficient if it's, if we're comparing it to something. Okay.
It's just the variance being larger or smaller, right?
Yeah, exactly. So if the variance of something is larger than another, then it's less efficient.
Okay, so to measure consistency, we see if the expected value of the parameter, like, as n approaches infinity, if it approaches 0, and then same with the, like, variance of
The
that?
bias and the variance.
Okay.
The bias. So we use the expected value to
Right.
find the bias,
Right.
and then for
Oh,
consistency,
so then
we're
we
looking at
look
bias.
At
and-
the bias, okay. That
Exactly.
makes sense.
Exactly.
This one is okay.
Right?
This isn't bad.
Estimator questions I think are very scary because there are lots of things in them, lots of scary numbers, but they're really pretty
I think
manageable.
they're actually hard because of the lack of numbers. Because it's just letters.
Well, in that
Like
case,
that.
I'm referring to scary numbers as letters.
They're the scariest of numbers.
Because those letters are just numbers. They're just representing numbers. Okay, and then part D. What is the variance of the estimator? Oh, wait, sorry, I skipped part C. Okay. Construct an alternative estimator. Theta hat 2. That is a function of theta hat 1 and is unbiased. How would we do this, team?
Ooh, I think I know.
Tell me.
Because we want the bias to be, we want it to be unbiased.
We
meaning
want it to be
bias
unbiased.
0. So can you just take the bias that we found from part A instead of equal to 0 and then solve?
Tell me what you get from that. Work it out. I'm saying like take a couple minutes real quickly, all of you, and try to work out the answer to this, and then we'll talk about it. That I would bring it back up here. Well, this should be true. This should be true. I would probably work with it from that point. I think it'll be easier to work with it from that
So
point.
those are equivalent statements.
In fact, you may not be able to look at it from here.
You would just get the theta
Yeah.
equals negative one.
Yeah,
Not quite.
not quite useful. I would use that. Yeah.
When I went into Dr. Price and asked him about this, he was saying that if you take the bias, you can multiply by the inverse, and that gives you.
Yeah, because actually.
That'll work. That'll work. So you're saying let's multiply this by n plus 1 over just the straight inverse?
N plus 1 times n plus over n plus 1. I think, or wait,
No, because I would still leave you with.
yeah,
So you're talking about
yes.
letting theta hat 2 be theta hat 1 times that thing at the end
Yes.
with theta replaced by theta hat 1. Because it can't exactly be a function of theta, right?
Well, so it would be theta hat 1 times the inverse of the bias. Okay. You should have that cancel out, but it's very interesting.
Possibly.
This is an estimate.
Yeah.
I'm gonna work with it from
It
this
was.
point because I think this is simplest because this is just straight algebra where I add over my estimator or I add over the thing I'm trying to estimate. This is theta hat 1, right, that we plugged in here. Or actually no, this was the expected value, so this is straight theta n plus 1. I just multiply over n plus 1. Add over the 1. Divide by the n. And this is theta hat 2.
How do you know what to solve for?
That's a fair question. For the most part in these questions, you're going to have two real variables, right? You're going to have the thing that you are estimating, right, that you're subtracting, and then you're going to have something that looks like it in the other term, right? And so you're trying to get this guy by himself, the thing in the term, because what we're trying to do is we're trying to find an equation that when plugged into this is going to cancel out everything except for
Oh, okay.
the thing that we're
Gotcha.
estimating, right? So we're solving for this. Yeah.
That makes sense.
In his key, he has, instead of theta, he has theta hat 1.
Yeah,
Is that right?
that is right.
And how does that happen?
Because we're making this, well, it has to be true because theta hat 2, according to the question, has to be a function of theta hat 1.
Oh, so that, just from the beginning, the variable.
So from the beginning, but, ooh, so now we get to find the expected value of this. Or, yes, we do get to find the expected value of this. So it is important that this is true, that this is theta hat 1, because when we go to the next step, when we go to the next step and we're finding the bias, we know what the expected value of theta hat 1 is, right? And so if we don't know what the expected value is of this variable, we can't plug it in when we do the bias. So if we move on to the next question, which asks us, I believe, to prove that it's unbiased.
It says to find the variance of the estimator using that. Part D.
Oh no, sorry. Just the second part of part C. We have to prove that this is an unbiased estimator. So if I find the expected value of theta hat 2 minus theta, what I'm going to get is the expected value of this guy, theta hat 1 times n plus 1 on n minus theta. The expected value of all this garbage is just this garbage because they're just constants. The only thing that the expected value actually applies to is theta hat 1. We know what the expected value of theta hat 1 is. It's this stuff. So let's just plug that in. and say, okay, great, this is equal to n theta minus 1 over n plus 1 times n plus 1 on n. Those cancel out, and we end up with n theta minus 1 plus 1 on n. The 1's cancel out, the n's cancel out, and this is just theta.
Okay.
To complete bias, so this was the expected value of theta hat 2, right?
Yeah.
So expected value of this, theta minus theta equals 0. It's unbiased.
That's not that hard,
It's not too bad.
if you know how to do
Yeah. Part D is where it might get a little bit saucier. So let's do that real quick. Part D asks to look at the variance of this new estimator that we have created from the dust. So variance of our thing, getting emails. We said this is theta hat 1, n plus 1 on n. So let's pull out some constants first. Let's pull out the n. We have to square it when we do that, right? So 1 over n squared, variance of this garbage. Variance of this plus 1 is 0, right? So we can just get rid of that. When we pull out this term, n plus 1 that's being multiplied, we have to square that. So we get n plus 1 squared over n squared. I'm just going to simplify that to be n plus 1 over n squared times the variance of theta hat 1. We already have the variance of theta hat 1. It was given to us from on high. Thus, we have n plus 1 over n squared times the variance of the first guy. Let's see if we can do some simplifying here. These terms are going to cancel out, so we're going to be left with theta over n squared. And then the question asks us if this is more or less efficient than the original. So we have to compare this to this. Which one of these is going to be smaller?
The one with
it.
n
No,
plus.
that's not what.
So
This
that's
one.
denominators.
Yeah.
Dividing by a bigger number every
Right.
time. So this will always be smaller.
So it will be more efficient?
So the original variance,
Okay.
the variance of the original estimator is more efficient, even though our new estimator is unbiased.
Okay, because the more efficient is the smaller.
Is the smaller one.
Okay.
So it's marginally more efficient. I would probably choose to still use our second estimator because it's unbiased and only slightly more, or only slightly less efficient. But cool. Does that make sense?
Yeah.
That whole process? Not too bad, right?
And I believe in Santa Claus now. He's
I-
benevolent.
Very benevolent. Yes, sir.
So just going back to part C real quick with
Yes.
constructed estimator. So once we've like found an estimator, we have to go through and prove that that is an unbiased estimator. Or
The-
once we like
Oh,
find
yeah.
that equation, like
You
once
have
we
to
do
show
that,
proof.
once we find the equation, can we just be like, cool, like you saw the math of like setting it all to 0, you saw I went through the process, is that fine?
So, I mean, the question here says, construct an alternative estimator that's a function of theta 1 hat and is an unbiased estimator. If I was grading your test and you just like did this work and spat this out, I would probably give you full credit. If I were taking the test, I would probably plug it back in and see if it worked, just to check, just to be sure. But yeah, for points, not necessary. Unless it's specifically requested.
And if it says, and prove that it's
Yeah.
unbiased, then you have to.
Then you have to plug it back Sweet. We're gonna go and look at this question anyway during the review, so easy peasy. Okay, we have 30 minutes or so left that we can use up if we're so desirous. There's one other question on the practice test. It's a review question from a homework question a while ago. It's not particularly difficult. We can do that real quick just to review, or if you guys have other questions in the practice test that you think would be more advantageous to go over, we can spend our time doing that instead. What think ye? Do we have any questions on the practice test?
I do. On the true and false question.
Ooh, true false, classic.
I didn't have any idea how to do number 4.
Number 4. x1 equals 1, x2 equals 2, and x3 equals 1 hundo. Rounded to the nearest whole number of the sample standard deviation based on unbiased variance estimator is 55. So what is our unbiased variance estimator? What's our equation for that?
1 over n minus 1, the summation of xi minus x bar squared.
Gut gemacht, as they say. Yeah. Right. X highlighted. Sweet. So this is our equation.
What is that? Where did that come from? I have 0 recollection.
This should be in your notes somewhere. Probably from the time that we talked about estimators.
Okay.
This is our estimator for the sample.
Y infinity?
Did I think that was just force of habit. I'm in Calc 2
Calc
right
2.
now. I do a lot of
Yes.
that. Do a lot of that to infinity sums. Just that.
And then, like from I equals 0 to n?
Yeah. Okay, sweet. There's no n in that. That should be I equals 1, I believe.
Calc is really messing with you.
Calc is really messing with me. The muscle memory is real. N equals 0 to infinity.
Remind, is that s squared equals that? Or just s?
Yeah, this is s squared. So, standard deviation is just, or sorry, normal variance is just 1 over n, sum of this stuff. And you may recall a lengthy proof that we did a couple weeks ago in which we showed that if we use this with sample data and not with population data, that it consistently is biased. And so,
Unbiased, you do the n minus 1.
yeah, in order to make things
memory is
biased,
flooding to my mind.
we do 1 over n minus 1. So I would memorize such equations because there is a reasonably high chance that there's some sort of true false related to that. I mean, how many true false are there on the final, like 10 or something? But like, isn't that what he said? Maybe not. Maybe there are fewer. But regardless, this is the type of thing that is convenient to write a true false question about. So there could be such stuff. Yeah.
I understand, well, I'll just have to look back on the proof, like the sample, you would do like 1 over n minus 1. But how come for like the population variance, you have to divide it by n? Like, didn't we learn that the variance, you don't divide anything by n, it's just like the equation you just wrote?
So when we were doing variances before, right, we did the expected value of the thing squared minus the thing squared, right? Well, how did we calculate this? We did each of the x values multiplied by their probability, right? We don't have any probabilities in our data sets, right? But we do have sample sizes. And so everything has an equal weight in a sample, right? My likelihood, if I've got 30 observations, my likelihood of picking out one of those observations is 1 in 30, right?
It's just like the same logic of like taking the average by like adding things up and dividing it by n.
Exactly.
Okay.
Exactly. It's the same thing. So 1 over n here represents our probabilities. So it's the same process we were doing before with variances of x squared times its probability, but since we don't have any explicit probabilities, we just weight them all equally in our equation. And since it's the same, it's just a constant that we can pull out of the sum and multiply everything by at the end.
Got
Right.
it. Thank you.
Sweet. Are there any other oh, yep,
Yeah.
Ella.
I mean, we could do the whole problem, but I have like a specific question on this problem. It's on number 2.
The second true false or
No,
second
sorry,
long
the
answer?
second long answer.
Okay.
My question is, they're testing a hypothesis to see if, like, what is it, the mean, like, one's higher than the other, or faster than the other. So when you calculate this, do you use the population variance or the sample variance?
Let's see. Let's read this. So the McMiriam's question.
Yeah, that
So
one.
McMiriam's is a large fast food chain with thousands of locations. Miriam, founder and CEO, wants to try a new process for preparing French fries. She pilots the new process in a random sample of 24 locations. Suppose the time per French fry batch under the original process followed a normal distribution with a mean of 15 minutes and a variance of 6 minutes. This was the population distribution. Wow, very clear. In the random sample of 24 locations that tried out the new process, average time per batch was 13 minutes with a standard deviation of 9. Perform a hypothesis test to see whether the new process is significantly faster than the old process. So let's see.
Because we have the population, we should use Z instead of T, correct?
Correct.
Okay.
Well, but
But it's
But if
24
it's under
locations.
30,
it does depend on what we use. So in the answer key, he used the sample standard variance, and so he used a t-test.
Okay.
Question.
Yes.
So if n is less than 30, do we always use the t-table?
No.
No. When do we not?
So we use the t-table when n is less than 30 and when we only have a sample standard deviation.
Okay, but if we have the population standard deviation, even if we have like only a sample of like 24, we use the z-table and not the t-table.
So long as the population is normally distributed, yes. Which for all intents and purposes on the test, all the populations are normally distributed.
Yeah.
In the answer key, he used the t-table and he used the sample variance. In my mind, since he gave you the population variance, it would be legal to use the population variance and the z-table.
The z-table, okay.
It would be fine to do either. You would just have to be consistent in which one you used.
Okay.
It could be either one.
You could use either. And you just want to be consistent.
Because I used the other one, like I used the population variance, and so I got something a little different. Not like, I didn't get like the critical value, the same thing, because I
Yeah.
did it by 9 or 6, so.
I would say, let's see, what's a good rule of thumb? If you have,
T-test on it, so, like,
if, I would say in general, if it gives you a sample standard variance, use the sample one.
If it gives you a sample
sample?
standard variance, use the t-table? Or use.
Well,
or
so use the sample
one.
and also the t-table.
Okay,
That would be my general rule
even
of
if
thumb.
they also give you the population standard deviation?
Yep.
Or standard variance?
That would be my thought.
Because what exactly is the purpose of them giving the
population
one here?
variance.
Because like, if we were doing a test on the variance, like
Yeah, if
That's-
if you're
that's
only
my-
doing
chi-squared
population,
test,
use
right?
Z. But you're saying
But
you
like-
do both and it's under.
That's my thought, is notice that question 2, it says 2A,
Alright.
and then there's no other part.
Yeah.
So I think originally there was a part B that asked about the variances, and that's
Okay.
why it provided both.
Okay.
That's my
Critical
hypothesis.
value is -2.50. And then the,
-2.50?
oh, that's like the one, I think he's comparing it against.
That's the critical value.
And then he got 3.266 as the like test.
Is this in 2A?
Yeah, 2A.
2.66 is the test?
Test statistic is 3.266. And then the critical value is 2.50.
Cause I used the T table and those were the numbers I got.
Yeah.
So it's, he used the T.
Okay.
Hold up, so I got a different test statistic.
That's
Oh.
my other.
But we,
Yeah, okay.
would we have points taken off if we happen to use the population standard deviation
In
and the
Z
Z
table.
score, like Z table?
I'm not entirely certain.
Okay, I will just.
I
So,
would
wait.
not, I would clarify with him though. Again though, rule of thumb, if it gives you the sample standard deviation, work with that.
And
And,
it's less than 30.
right,
From what I asked him in the, just a pleasure, he was saying like, as long as you like clearly state which table you're
Yeah.
using, then like, it's okay, or whatever, but you have to like, make sure that you're
Be
saying,
obvious about
like,
it.
hey, I'm using a T
And-
distribution for this.
I would also say with that, like, give reasons why. You know, be like, I'm using the Z table because I was given the true population variance
Mhm.
and it fits these other conditions, and so I'm using a Z table.
It's normal
And-
distributed.
Yeah, and if you tell me that and you put that down on the test, then I would say likelihood of you losing points is extremely low, even if the test answer key uses the T table.
okay.
So,
Okay, that's helpful.
And it should give us the same conclusion. Oh, I guess it depends
In-
if it's like a,
I believe in either case here you'll still reject the null hypothesis.
would there be cases where you would,
You do.
you fail to reject with like a T stat and then reject it with a Z score?
On a well-designed test,
No.
they will be, yeah,
Same
on, like,
conclusion?
and test as in like the test itself that you're taking.
Right,
On a well-designed test, it won't be close.
okay.
It will be pretty clear whether you reject or not, you know, it won't be close either way.
Sounds good.
That's helpful.
It's like 0.02.
Yeah, if it's like barely off, like your critical value
You're
is
like at
1.96 and you're at like 1.95, like, yeah, that will probably not occur. Okay, do we have other questions on the practice test?
Just like a general question, I just
Yeah.
want to try and make sure I have my mind wrapped around all the different types of test statistics and tests and how to use each of those. So would it be okay to like write them all out on the board?
Yeah,
Just
for sure.
see like everything.
Thank
Oh, so I might like try writing out what I can remember.
Every formula we would ever need.
Yeah, that's what I was
Going
trying.
forward.
Yeah, go through the test. and
Patrick,
tell
would
us
you
more.
actually be so kind as to write on this board so that
Yes.
it's on the video
Go
stream?
through all of calculus.
Oh, there it is.
There it is.
Gotcha. Can I erase all this?
Yeah.
Okay. So the one for this problem that we just used was sample mean minus population over
Skipping the question entirely.
the square root of the sample variance divided by n. And this was distributed according to t with n minus 1 degrees of freedom?
Correct.
Okay. And what do we call this?
That would be a T-stat specifically.
T-stat.
A T-score, T-stat.
And we would use that to find the confidence interval.
This
The bottom.
is for a hypothesis.
Hypothesis, that's a
Yeah,
test
but we would
statistic
use
for it.
the test statistic on the bottom to find the.
You do X.
Oh, you're talking about
I'm
this?
talking about like the denominator.
This would be, yes, this would be used as your margin of error. Part
Right.
of your margin
Part
of error.
of
for your-
multiplied.
Multiplied
that-
by a
that
Z-score or
value, the
T-score.
Z-score, yeah.
Okay.
And this is when you don't know population variance.
Yes. If you don't know the population variance and your sample size is less than 30, T-stat.
Okay. So then there's also a z-stat, which is x bar minus mu over s? or just sigma?
Sigma.
Where sigma is the population. Okay. And so you have to have the population given.
And that should still,
Should be over n still, right?
Would
it's
it
still
be
over
a-
n.
It's
It's,
still
so
the square root.
it will be square root of sigma squared over n, or you can do sigma over square root of n.
That makes sense.
Okay. So we never just have x bar minus mu over sigma.
Because this is all about samples, right?
Yeah.
Yeah.
And this is an estimator in both cases, so.
Okay. And this is going to be normally distributed.
Yep.
0 and 1. Okay.
And that means if we know the population.
Yeah.
If you know the population variance, or if sample size is greater than 30, you can always use a z-stat.
We've also seen mu1 minus mu2 over.
Just to clarify the last one.
Mhm.
Is it or is it and? You have to have both for the z-score?
Or.
Okay. Thank you.
You get it right on the thing, you know.
So this is for used for difference in means,
Yes.
correct? Okay. And this. will
You're
be-
missing something on your numerator for this.
Mm.
You've got mu's, but you need. Yeah.
Okay. Sorry. Okay. This is for used for difference of means. And will this be normally distributed or?
So
because you can't really.
you can do it in either case here. 99.9% of the time, this will be this will spit you out a z statistic.
Okay.
But if you don't know either of the sample or either of the population variances, and both your sample sizes are less than 30, then you would use a t statistic
Okay.
for this. But like I said, 99.9% of the time, z-stat for difference in means.
So it's also normally distributed to 0 and 1.
Yep.
Okay. Is this helping other people, by the way?
Yeah.
Okay. Okay.
Yeah, keep going.
I don't want to hog the time, but if it's helpful,
I
we
had
can keep
another
going.
question for the difference of means. Do you use the population variance or like the sample variance or just whatever they give you?
So that's kind of what we were talking about just a little bit. It will be what's given. It will normally give you either both sample variances or both population variances. And most of the time, it will be population variances.
Okay, thank you.
And if it's not population variances, then you should have both these be higher than 30, so you can apply
Yeah.
central theorem.
Exactly.
Okay. Let's see. What else have we seen?
The proportion.
We've seen.
Yeah.
Oh, proportion. That's right. I'll do that real quick. So that's p times 1 minus p over. Hold up. What was proportions again? For the test statistic.
That's part of your denominator.
Yeah. On the top, it would be p hat minus p.
Minus p. Okay.
And then depending on whether we're finding, well, I guess in this case, we would use p hat.
It's P.
No, it's just P.
They give you.
Yes, because it gives you the, yeah, it's a hypothesis. Yeah,
Yes.
there we go.
Okay. So this is proportions. And will this be normally distributed?
So long as the sample size is big enough, it will be
Okay.
normally distributed. If you have, again, I don't anticipate this on the test, but if your sample size is less than 30 for a proportions hypothesis test, you just can't do it.
You can't do it.
Okay. Okay.
That'd be awesome if that was on the test.
Yes.
Well, actually, let me amend that. You can't do it if it also doesn't specify that the population is normal. If the population is normally distributed, you can have less than 30 and run the test.
Okay.
But, yeah.
Okay. Cool. So that's proportions. I'll keep going here. And the one is n minus 1 s squared over sigma squared. This will be distributed according to chi squared with n minus 1 degrees of freedom.
Yep.
Okay, and this one is called what? Just variance estimation, or?
Yeah. Yeah. Variance estimation, variance.
And that one's if-
I would just, I mean, up above we said t-stat and z-stat. I would just say like
Sample variance,
chi-square value,
but they don't give us.
chi-square test.
Or you can use it to solve for the population variance, that's usually, well, I guess it just depends. But if they
Okay.
give us just the variance.
Are there any other test
I know.
statistics that we use? That we've seen and stuff?
The only other test that I believe we've talked about is difference in proportions. Did we do difference in proportions?
Yeah, we did.
That's right.
That one,
Which is just a nice mixture of difference in means and proportions.
Is that
So,
one that's
what
like
is it?
p hat